Our aim is to study about the local maximum and local minimum point of a function, of a differentiable function. I assume that the function is differentiable at every point of the domain, and I will take the domain as an interval like a comma b. Okay, and we already proved that at a local maxima or local minima, the first derivative must vanish. That is, if x naught is a local maxima or minima of a function f of x, then f dash x naught must be equal to 0. The question is it necessary that such a point, that is a point at which f dash x naught is equal to 0, is it necessary to be a maximum point or a minimum point? That's the first question. And how to distinguish between the maxima and minima? First, we define a stationary point. A point x naught is said to be a stationary point or a critical point of a function f of x if its derivative vanishes at that point, that is f dash x naught is equal to 0. But all this, as I mentioned, at a local maxima and local minima, f dash x naught is equal to 0. So at a local maxima and local minima, definitely the point will be a stationary point. But all stationary point need not be a maxima or minima. Why? Because you can see this figure. Here, what happens is, say this particular point is the uh, point x naught. So at this point x naught, you can see that the tangent is getting parallel to the axis, real axis. So at this point, definitely f dash x naught is equal to 0. But you can see that it is neither a maxima nor a minima, because this a point is a maxima if it is increasing from the left side and decreasing to the right side. If it's a minima, it should decrease on the left side and increase to the right side. This is everywhere increasing, right? It's from the left side to x naught. If you go, you can see that the function is increasing, and to the right side also it is still increasing. Such a point is called a saddle point. So all stationary points need not be a maxima or a minima. So you cannot guarantee that if f dash x naught is equal to 0, x naught is a maxima or a minima. It can be neither. So we have seen that a point x naught at which f dash x naught equal to 0, that's called a stationary point. It need not be a maxima or a minima. Okay, so the next question is, can we guarantee the existence of a maxima or a minima using the derivatives of a function? And that is where the famous second derivative test helps us. It says that suppose you have function f from ab to r is twice differentiable in the open interval ab. And suppose that x naught is a point in ab, the open interval ab, such that f dash x naught equal to 0. That means x naught is a stationary point. And suppose that the second derivative is less than 0. So the second derivative at the point x naught is a negative number. Then you can conclude that x naught is a local maximum point of the function f of x in the interval a comma b. Of course, in the interval a comma b, there can be plenty of local maxima, and also there can be local minima. And the condition for a local minima is that first condition should be there, that is the point x naught should be a stationary point. Further, if the second derivative at x naught happens to be a positive value, then you can ensure that the point x naught is a local minimum point. The question is why these two conditions imply that the point x naught is a local maximum point of the function f of x in AB. So we have seen that at every local maxima, f dash x naught should be equal to 0, and of course at local minima also. So this condition helps us to locate the points at which there is a possibility that the function gets a local maxima or minima. We have f double dash x naught is equal to 0. What is f double dash x naught? It is the derivative of f dash x naught, right? Now suppose that f double dash x naught is negative. That means the limit of x tends to x naught, f dash of x naught minus f dash of x divided by x naught minus x is less than 0. Okay, so the limit is strictly less than 0. That implies the function should be less than 0 in a neighborhood of x naught. That is f dash x naught minus f dash x divided by x naught minus x should be negative in a small neighborhood of x naught. That is x very close to x naught. That means what? If this quantity is less than 0, that means the fraction is negative, right? So the sign of the numerator and sign of the denominator should be different. That is, if f dash x naught minus f dash x is positive, then x naught minus x should be negative, and vice versa. Okay, so whenever x naught is less than x, it so happens that f dash x naught is greater than f dash x. Okay, so when you take 2 points, like first point and second point, f dash x is, so this is x naught and this is x. So f dash value at x naught will be uh, bigger than f of x value. So that's why I am saying that f dash x is a decreasing function near to x naught. Okay, so that means the f dash x gives you the slope of the curve, the slope of the curve. And you know that at x naught, the slope is 0. That is, the tangent is parallel to the x-axis. So at x naught, the tangent is going to be like this. So its slope is 0. So to the left side, it should be having a positive slope, and to the right side of x naught, it should have a negative slope. That means to the left side of x naught, the function should be increasing, and to the right side of the point x naught, the function should be a decreasing point function. So that forces that the function should increase from the left side and decrease to the right side. So that makes this point as a local maximum point. Okay. So similarly, you can say that at a point x naught, the local minimum happens if it's a critical point or a stationary point, and if it's a f double dash x naught is positive. That also you can similarly do like this. You assume that it is greater than 0, then both should be of the same sign. So that means f dash x should be an increasing function. So that means on the left side it should be negative, and at x naught it should be 0, and to the right side it should be positive. So that means it has to decrease, then become 0, and then increase. So that at a point at a point x naught at which f double dash x naught is negative, the function should have a local minima. So the idea is basically that if f double dash x naught less than 0, then the curve should increase on the left side and decrease to the right side, creating a local maximum point at x naught. But it is not true that at every local maximum point these two conditions should be satisfied. Okay. So the first condition must be satisfied, but the second condition need not be always true. That is, there can be local maximum point at which the f double dash x naught is strictly less than 0, but it cannot be positive. If it is greater than 0, it must be a local minimum point, and if it is strictly less than 0, then it will be a local maximum point. But there can be local maximum point at which f double dash x naught is equal to 0. For example, you consider a function whose graph is like this and take a point here. That image I have denoted by a red dot here. So at this point, you can see that the function has got a local maxima. It is not only having a local maxima at this point, to the left side and to the right side, I have drawn the curve to be a line parallel to the x-axis. At each of these points, there are local maximas for the function. There are infinitely many local maxima to the function around the point, around this dotted point. Okay. So what happens is, you can see that in the neighborhood of this particular point, and tangents are entirely parallel to the x-axis, or the slopes are continuously 0. So what happens is f dash x is equal to 0 from this point to this point, or that means in the from the domain, if you look from this point to this point, f dash x is entirely a constant. That means f double dash x naught will be 0 for this function at the point x naught. So this is an example to show that double dash x naught, even if it is equal to 0, then also it can be a local maxima or a local minimum. For a local minima, you have to invert the curve, and if you take a curve of the shape u with this lower side parallel, then you can see that the point at which f double dash x naught is equal to 0 can be a local minima also. Of course, it can be a saddle point. So if f double dash x naught happens to be 0, you cannot conclude from the function's derivative. Then you have to go for the value of the function near to the point x naught and see the geometry. And we say that a point x naught is an absolute maximum of f of x, that is absolute maximum or global maximum of f of x, if f of x naught is the biggest point in the domain. That is, every other x will have f of x less than or equal to f of x naught. It is not concentrating on a particular local domain. If it happens for the entire x in the domain, then we'll say that f of x naught is the absolute maximum or global maximum. Similarly, you can define the global minimum at a point x naught if f of x is greater than or equal to f of x naught for every x. That means f of x naught is the smallest point or smallest image. In that case, we call it as an absolute minimum. Okay. So for finding the local maxima and absolute maxima and all, first you have to find the local maxima. That is, first you find the critical points and then classify the critical points according to the behavior of the second derivative. And for finding, so that is enough for finding the local maximum points if f double dash x naught is not happening to be 0. And to find the absolute maxima and absolute minima, you need to check the boundary points also, because at boundary also the maximum, absolute maximum or absolute minimum can happen. Whereas at that point, the function need not have a stationary point. For example, if you consider the function defined using this graph, then you can see that there are plenty of local maxima. Say, for example, this point is a local maximum point, and this is also a local maximum point because this value is highest value, and this is also a local maxima, whereas this point is a local minima, and I'm calling this point as a local minima, and this is a minimum value. This value is f of x naught is called the local minimum value, and similarly there exists a local minima at this point. But what is the peakest value of the function? That is happening at this point, right? So this point, that is b, f of b is the highest value of the function. So we can say that the absolute maxima is happening at b, and the lowest point, the image happens to be the lowest at the point a. So a is minima because f of a is the smallest value of the function in the neighborhood in the given domain. Okay, so in the entire domain, this a and b are the absolute maxima and minima, whereas there are local maximas like this one, say call it as x1 and x2. x1 and x2 are local maxima, whereas b is the absolute maxima, and this x naught and say x3 are local minima, whereas a is the uh, global minima or absolute minima of this function. Okay, so for finding the absolute maxima or absolute minima, you need to first locate all the local maxima and then go for the values at the endpoints and check which is the highest, and that highest value will give you the absolute maxima. Now let us see an example. Find the extrema. Extrema means it includes both maxima as well as minima of the function f of x equal to x cube minus 3x square minus 4 in the interval minus 10, 10. So this is A and this is B. Okay. So function is given and its domain is given as minus 10, 10. So we will find all the local maxima, local minima, absolute maxima, and absolute minima. Okay. So first step is to find the critical points. So you put f dash x equal to 0. That gives you 3x square minus 6x minus 0 equal to 0. That is x equal to 0 as well as x equal to 2. So x naught equal to 0 and 2 are the stationary points. So you find f double dash value at 0 as well as 2. So f double dash 2 is equal to 6. It's a positive value. So you can see that at 2 there is a local minima. Now f double dash 0 is equal to minus 6. If you substitute 0 here, you can see that it is minus 4, right? Okay. F double dash, if I take, it will be 6 minus 6. So 6, 6 minus 6. So it is minus 6. So it is negative. So there is a local maximum at 0. So the local maximum at 0 and the local maximum value is f of 0 is equal to minus 4, and the local minima, which is at 2, and the local minimum value is 8, minus 8. Okay, the function is completely in the negative side, and the local maximum value is minus 4 and local minimum value is minus 8. So the local maxima and local minima have been located along with their values. Now let us go for the absolute maxima and absolute minima of the function. Now you see the endpoints of the domain. So there is an endpoint at a 10. So you calculate what is f of 10. It happens to be 696. F of 10 is going to be 10 cube minus 3 into 10 square minus 4. So it happens to be 696, which is a positive value. And f of minus 10 is equal to, substitute minus 10 here, you get minus 1304. So it's a huge negative value, right? So the function, the global maximum value of the function is at the point 10, because out of the local maxima and the boundary values, the peakest value is of the function is 696. So the global maximum is at 10, and the global maximum value is 696. And the global minimum is happening at -10, and its value is 1304. Okay, 4. This is a typo. So f of -10 is -1304. Okay. So we have located all the global maxima, local maxima, global minima, and local minima also for this function. Geometry of this function, if you plot the function, you can see that the function is going like this. At -10, it is having a minus value, negative value, huge negative value. It is -1304. And then there exists a local maxima at 0, which is -4. And then at 2, it has a local minima, so it comes down, and it comes down and takes the value -8 at 2. And then again at 10, it goes to a very huge value, 696. So this is going to be the or an approximate shape of the graph. Okay. So this is also a use of this study about local maxima and absolute maxima, etc. You can get to know the shape of the curve using these ideas. Thank you.